All right, I'm going to do some examples with you with homonuclear diatomics and how to draw molecular orbital diagrams. Remember that these are energy level diagrams, so we need to indicate the energy axis, which I'm doing now. Okay, so that's an increase in energy. And now let's construct the molecular orbital diagram for nitrogen. So I'm going to start with one nitrogen atom on the left-hand side. And we know that we have a 2s orbital here, and we have 3 2p orbitals like this in terms of increasing energy. Okay, the electron configuration for nitrogen is essentially 2s2 2p3 because the atomic number is let's see, 257. Okay, the atomic number is 7, but we're not going to consider the 1s electron. So let's take a different color pen, and on this side we're going to do the second nitrogen. Remember that we draw it on the same energy level, this 2s orbital roughly on the same energy level. Oh goodness, sorry, my pen seems to be hanging a little bit. Let me just erase this quickly and start over. Okay, so we've got 1, 2, 3, and these are 2p orbitals, and the same number of electrons. There are 5 in the valence orbitals. All right, so now let's construct the molecular orbitals. Okay, so now we've got in the middle, we've got N2. Now, the 2 atomic orbitals must give us 2 molecular orbitals from the 2s orbitals. Okay, so we've got one down here that's of lower energy and one up here that's of higher energy. This is the bonding orbital. This is the anti-bonding orbital. Okay, so they both come from the s interaction, the 2s. And remember that the bonding is gerade for sigma, and this anti-bonding is ungerade. Okay, so where do the electrons come from? Well, they must come from each of the atoms. So I'm going to put one from that atom and one from that atom, and then fill up this one there, and this one there. So we have 2 red ones from this red one here, and 2 green ones from this green one here. And we're kind of, let me just link them together so that you can see that these come from the s orbital interactions. Okay, so it's just a rough indication of where these things are coming from. All right, now let's have a look at the 2p orbitals. And the 2p orbitals in this case, remember that for nitrogen, there is S and P mixing because the S and P orbital energy gap is quite small. So that means we need to draw the 2 pi orbitals first for the bonding interaction at the very most, okay? And then we draw the sigma. So this is the pi bonding. So it'll be from the P, and it'll be ungerade because that's what happens. And then this one will be the sigma bonding from the P orbitals. Let me just get rid of this and redraw this for you. So this is from the S, and this would be gerade. And then at the top, it's as you would normally put them. So we put the 2 pi star orbitals from the P orbitals. These will be gerade. And then the one at the top here, this will be sigma star from the P orbital, and this will be ungerade. Okay, so then let's place the electrons. All right, now we have to place 2 electrons from the one atom. So let's that one, and then we take 2 green electrons from the other atom, that one and that one. And now we have 1 green and 1 red left. So we've got 1 red and 1 green, and then the top is empty. So if we just draw this roughly, just link them together. This is what we're going to sort of look at. There we go. And this is what the molecular orbital diagram should look like for nitrogen itself. Now, let's calculate the bond order. Okay, so before I do that, please notice that there are no unpaired electrons anywhere. Okay, so that indicates that this material is something called diamagnetic, which means that it will not have any magnetic properties and it will not deflect a magnetic field. Okay, if we calculated the bond order, all right, so bond order, according to the formula, is equal to half the number of bonding electrons minus the antibonding electrons. We can do it exclusively for the valence electrons. You don't need to worry about the 2s orbital in this case. The valence electrons are simply the electrons in the 2p orbitals. And what we end up getting is we have 1/2. And if we look here, the number of bonding electrons, there are 6 of them in total. So that's 6 minus the number of electrons up here is 0. So 1/2 of 6 is equal to 3. The bond order actually tells us something about the Lewis structure, which if I draw this, will give you N triple bond N. And that's how we deal with the molecular orbital diagram for nitrogen. Okay, let me move up the screen and we'll do the next example, which will be for oxygen. Okay, so let's do oxygen now. All right, O2. Remember, we need to draw an energy indicator. Always important to draw the energy indicator. All right, and again, we'll go with oxygen down here. And we've got a 2s orbital, and we've got 3 2p orbitals, and we'll choose the other atom on this side here. Oxygen, we need to put them on the same level. That's 2s, and we need to put these ones roughly on the same level. These are the 2p's. Now we need to consider the number of electrons. We know that with 2s2, and we've got 2p4. So we fill them up like that. And let's do the green one. It's going to be exactly the same. So I'm just going to do this. All right, now we can construct the molecular orbitals for oxygen, where we've got one bonding and one antibonding. So this is the sigma bonding from the s orbital, which is Gerada. This is the antibonding orbital from the s orbitals, which is Ungerada. Okay, and again, you can see this is fairly easy to do. One electron from each, one going into the bonding orbitals first, and then into the antibonding orbital as follows. Okay, and if we just link them up together, you'll see that that comes from, sorry, my linking is not very good. Okay, so we can see that those orbitals come from the 2s. Right, now let's go to the p orbitals. For oxygen, we don't have s and p mixing because the gap between the s and p orbital is much larger. So we can do it in a conventional fashion where we say we have the sigma p, and it is Gerada, and then we've got 2 pi orbitals. This is pi from the p orbitals, and these are Ungerada. And then we've got the pi star, p Gerada, and then the last one is the sigma star from the p orbitals, and that is Ungerada. Okay, so we roughly have the links to the orbitals from the p orbitals of the atomic orbitals. Okay, now let's fill them up. All right, so now we must first fill from a red electron. Okay, and then we take a green one. Okay, so that's one from each. Then we can take one from the red into each one, and one from the green into each one. And that means we've used up 6. So we've got 2 more electrons left. Okay, so what happens here is these go into the pi star orbital, one red and one green. Right, now you will notice something. There are unpaired electrons here, and they're in the anti-bonding orbital. Okay, so this means that this material is paramagnetic. Okay, which means that it is affected by a magnetic field because of these unpaired electrons here. And if we are to work out the bond order, all right, we can do that. We have bond order is equal to 1/2 of the bonding electrons minus the anti-bonding electrons. So we'll get 1/2. How many bonding electrons do we have? Let's look at the valence set only. We have 6 minus 2 anti-bonding electrons in the valence set. That gives us 6 minus 2 is 4. Divided by 2 is 2. So therefore, if we were to draw the Lewis structure, we would draw a double bond between oxygen. And so with molecular orbital theory, we explain not only the number of bonds between the two atoms, we also explain its physical properties as well. If there are any more questions about this, the homonuclear diatomics are a lot easier to do than the heteronuclear, but I will explain that in another lecture, in another video.